Welcome friends. Today we talk about Claudius clapeyron equation. Okay. Before that, we must know some concept. This is some coefficients. Okay. Okay. The coefficients are, just wait. First one is the volumetric expansivity, isothermal and isentropic compressibility. Okay. Those are the main heading. Volumetric expansivity and compressibility, isentropic compressibility, isothermal and isentropic compressibility. Okay, what is isothermal? Isothermal process during temperature remains constant, and isentropic process entropy remains constant. Okay, compressibility means the compression. The during compression, volume decreases, pressure increases. Which is one type of compression. Then another type of compression is phase changing process. And if we drop down the pressure, the gas is comes to the liquid. That then again we create the vacuum. Then the liquid phase comes to the solid phase. This concept, according to this concept only, the LPG, the liquefied petroleum gas, the gas is stored in a gas cylinder. Okay, this is also another type of compression. Okay, which is called vacuum compression. Okay, but here they are telling the compression means if we reduce the volume, the pressure increases. Okay, but in vacuum compression, pressure reduces. Okay, then the equation of state for any thermodynamic system is expressed the function, the main important function. Main important function is for a thermodynamic is function of PVT, pressure and volume and T is equal to 0. For example, the gas equation is PV equal to RT. PV equal to RT, which is temperature is a function of P and V. Pressure is a function of V and T. And volume is a function of V and T. Okay, please understand. Okay, pressure is the function of, for example, 5 into 3, which is equal to, sorry 5 into 5 into 6, which is equal to 3 into 10. Consider this. Then 5 is equal to 3 into 10 by 6, which means 5 is a function of 3 comma 10 comma 6. Okay, 5 is a function of with the appropriate shape. Okay, similarly I told pressure is a function of T and V, similar manner. Okay, similar structure. Okay, but the total PV minus RT, which is equal to what? Okay, this is the equation. The function of PVT is equal to pressure is the function of Vt, volume is a function of P and T, then temperature is the function of P and V. Okay, this is individual functions, but the function of PVT, LHS minus RHS, which is equal to 0. The main important parameter. Okay. Then based on the differential formula, the function of PVT equal to 0, which satisfies dou P by dou V at temperature constant, dou V by dou T at pressure constant, and dou T by dou P at volume constant, which is equal to -1. The product of the partial differentiation of individual component, the product of partial differentiation of individual component, which is equal to -1, or perfect differentials. Okay, this is called cyclic relation. This equation is called cyclic relation. If we satisfy any equation satisfies the cyclic relation, then must prove that concept. Okay, which is the cyclic relations, the product of differential, which is equal to -1. Okay, so this is one type of main important relation. In future we can use this relation. Then another is coefficient of volumetric expansion. Next, that the coefficient of volumetric expansion beta is defined as the ratio of fractional change in volume to change in temperature when pressure is kept constant. Fractional change in ratio of fractional change in volume is dou V by V is a fractional change in volume. This change in volume divided by original volume, total volume. Change in volume divided by total volume is called fractional change in volume to change in temperature at constant pressure. Is called coefficient of volumetric expansion. Okay. In other words, the coefficient of volumetric expansion is indication of change in volume with respect to change in temperature, while pressure remains constant. Okay, it's also called coefficient of thermal expansion. Okay, then which is one word. Coefficient of volumetric expansion is equal to 1 by V. It's a dou V by V into dou T. Again I rewrite 1 by V into dou V by dou T at constant pressure. Okay, then next, coefficient of isothermal compressibility. Coefficient of isothermal compressibility. Okay, the top heading only tells the concept giving the process temperature equal to constant. Okay, therefore that ratio K is defined as the ratio of fractional change in volume to change in pressure when temperature remains constant. Okay, volumetric expansion is fractional change in volume during to temperature at the pressure constant. Here coefficient of isothermal compressibility, here the fractional change in volume to change in pressure at temperature remain constant. Okay, it is called coefficient of isothermal compressibility. Okay, then K is one symbol, and final is isentropic compressibility. Therefore, we have three coefficients: one coefficient of volumetric expansion, and coefficient of isothermal compressibility, and third one is coefficient of isentropic compressibility. Volumetric expansion beta, which is equal to 1 by V into dou V by dou T at the pressure constant. Isothermal is 1 by V dou V by dou P at temperature constant. In isentropic compression, here the entropy remains constant. Okay, therefore isentropic compressibility alpha is the ratio of fractional change in volume to change in pressure when entropy remains constant. Same. So alpha equal to -1 by V dou V by dou P at S. The minus symbol is when pressure rising, volume decreasing. Therefore, that 1 by V into dou V by dou P is isentropic compressibility. Okay, these things we must know. Three coefficients beta, K, and alpha. Beta volumetric expansion coefficient, K isothermal compressibility, and alpha isentropic compressibility. Okay, three coefficients are related to the change in volume with respect to pressure, temperature, entropy, those things also. Okay, you must know these things. Then we can directly go to the clapeyron equation. The Clausius-Clapeyron equation. The Clausius-Clapeyron equation relates saturation pressure, saturation temperature, and enthalpy of vaporization and specific volume of two phases of saturated fluid during phase change. Okay. First, what is saturation? Which is our fourth unit. Consider the water. The water having exist three phases. In real world, the water exists in three phases, in different phases. Okay, all three phases in available. No, all three phases doesn't available in a single place, but in Earth, all phases of water is available. Okay, in different places. Okay, first water is solid. The polarized places, the solid and hill stations, top of the hill, the water is available in the solid ice. Okay, then in our native place, Koilpatti, Thuthukudi, Tirunelveli, there is water is available in the liquid phase. Okay, in air having moisture. Okay, the atmosphere air having moisture. Everybody first we know that air having certain moisture. Okay, that moisture, if we want to see the moisture, then do an experiment. If go to the shop and buy a cool drinks and put it to the atmosphere, the cool drinks having lower temperature, the outer bottle, the outside of the bottle, in a certain period of time, some dews are formed. The dews is where from? The dews are attracted from the air due to the low temperature of the cool drinks. Okay, which tells internally, indirectly, the air having moisture in the form of steam. Okay, this is another phase, steam, vapor. Okay, therefore the water having three phases. One is solid, liquid, gas. Okay, in major, the water is available in liquid phase. Okay, minor, secondary, the water is available in solid phase is second, and third is water is available in the gaseous phase. Okay, the saturation means the for particular instant, the ice to water and water to steam, the conversion period during one phase to another phase is a conversion phase change process called phase change process. Phase change means the change of phase. For example, solid to ice to water, or water to steam, heating process. Okay, or in reverse, water to ice, freezing process. Okay, during that phase change process, the word is mean saturation. Okay, for example, if the water saturation, the freezing point is 0 degrees Celsius. If we have 1 liter of water, if you put the freezer, the temperature of the water is continuously decreasing up to the 0 degrees Celsius. In beyond that, the temperature doesn't change. Up to the all drop of the water is converted into the ice. This duration is called phase change duration. Okay, during that phase change, temperature remains constant. Then once the all liquid particles are converted to the ice particle, then temperature drop. Similarly, the same manner, if you boil the water, then up to the 100 degrees Celsius, water temperature is continuously rising. Then afterwards, the water is starts to change its phase from liquid to gas. During that time also the temperature remains constant. Okay, this also this process called vaporization. Okay, one is freezing, another one is vaporization. Okay, at that time the temperature and pressure remains constant. Okay, but one difference is initially we have 1 liter of water. The phase, initially the phase change is starts at that time 90% water, 10% steam, and particular time going, then 50% steam and 50% water, and in the end of the process 100% steam, which means the all liquid droplets are converted into steam. Okay, this is called quality of a particular product, quality of phase change. Okay, or dryness fraction. Dryness fraction means the dryness fraction is the mass of a steam divided by total mass of the substance. For example, I explain again. Put water in a heating pan, the heat is transferred, then it reaches the 100 degrees Celsius. The water starts boiling, then after when it reaches the 100 degrees Celsius, the temperature remains constant. This temperature is called saturation temperature. During that time, the phase change occurring from water to steam. Okay, when time increases, the water quantity continuously decreasing, which means the steam is continuously generated. At that time, all water droplets are removed from the pan and escape in the form of steam. Okay, therefore initially full of water starts, that means starting of boiling started. Okay, then increase of time, continuously water level continuously reduces and steam level continuously increases. Okay, a particular instant completely all liquid droplets are is converted to the steam. Therefore this is the volume of the liquid and volume of the gas. Initially volume of the gas is full, finally volume of the initially volume of the liquid is full, and finally volume of the gas is full. Okay, during this process is called phase change process. In that time temperature remains constant. Okay, from that I tell X, quality of our dryness fraction. The dryness fraction is how much dry this steam, how much amount of steam is generated from the water. Okay, that value is in between 0 to 1. Initially Vf means all the particles are available in the liquid form, therefore X equal to here 0. Then Vg means all the liquid droplets are converted into steam, therefore here dryness fraction is 100%. Okay, these things are called the phase change process and properties of few substances, which will be discussed in the next chapter. Okay, but we must know saturation temperature and saturation pressure. Phase change temperature, phase change pressure, and enthalpy of vaporization is during that phase change process also we supply some amount of heat. Okay, that heat is named as enthalpy of vaporization. Okay, that heat is used to change the phase from one phase to another. Okay, is called enthalpy of vaporization, and specific volume is Vf Vg. Okay, two phases we must know. Then the Claudius clapeyron equation relates these things: Vg, Vf, enthalpy of vaporization, and pressure, temperature. We can relate these things. Okay, then we come to we go to the relations. First we ds equal to S is the function of t and v. S is the function of t and v. First, take the relation S is the function of t and v because pressure is a constant one. In that Claudius clapeyron relation, during phase change process, pressure remain always constant. During phase change process, pressure always constant. Okay, pressure doesn't change. Okay, therefore S is a function of t and v. From chain relation, ds equal dou s by dou t at constant volume dt plus dou s by dou v at constant temperature dv. Okay, during the phase change of two substances, the saturated temperature remains constant. Okay, saturated temperature also constant. In previously I tell, okay, during phase change process, first pressure remains constant and temperature also remains constant. That is only we can tell the boiling temperature is 100 degrees Celsius and freezing temperature is 0 degrees Celsius. Okay, it's a constant one for a particular pressure. Okay, in pressure increases or decreases, the boiling temperature also increases or decreases. Okay, then the saturated temperature remains constant. Thus, dt equal to 0. Therefore, ds equal to dou s by dou v at constant temperature into t. From this, ds by dv equal to dou s by dou v at constant temperature. ds by dv equal to dou s by dou v at constant temperature. From this relation, we put dt equal to 0. Okay. Then cross multiplication, then ds by dv equal to dou s by dou v at constant temperature. Okay, then using third Maxwell relation. Okay, remember every time in that unit, every time you remember the Maxwell relations. Then from the third Maxwell relation, dou s by dou v at constant temperature, which is equal to dou p by dou t at constant volume. Then which is equal to ds by d. Okay. Then for two phases of two substances in equilibrium, the pressure and temperature are independent of specific volume. Okay, this derivative equation 9.74. 9.74 is this. Okay, may be written as dou p by dou t at constant volume equal to dp by dt at saturation process. Dou p by dou t at constant volume can be rewritten as dp by dt at saturation direction. Okay, phase change process time. Okay, then dp by dt saturation, which is equal to ds by dv, is sg minus sf. Sg is gaseous phase, sf is liquid phase, and dv equal to vg minus vf is equal to sfg and vf, called as sfg and vf. Then the pressure and temperature during phase change remains constant. Q equal to H2 minus H1. Q equal to enthalpy difference. Okay, Q equal to, remember the nozzle and turbine equations. Q equal to H2 minus H, steady flow energy equation. From this, during phase change, the enthalpy changed. Therefore, Q equal to H2 minus H1. This also HTG minus HF equal to HFG. Okay, then Q equal to TDS. Q equal to TDS. In previous time, Q equal to TDS. From first second law of thermodynamics, TDS. Then Q equal to T into Sg minus Sf. Then Sg minus Sf is what? Sfg. Okay, therefore Q equal to T into Sfg. Okay, then Sfg equal to Hfg divided by T. From this, Q equal to Hfg. Compare this, Hfg equal to Q, therefore Hfg equal to Tsfg. From this, Sfg equal to Hfg divided by T. Substitute the things. dp by dt saturation equal to dp by dt at saturation is only for saturated type. Okay, it's a main concept. Okay, dou p by dou t at constant volume can be rewritten as dp by dt only phase change duration. Okay, in remaining durations, partial and direct derivatives are not same. Okay, so only for phase change time. Okay, therefore only I can put the SGSF. SG is gas, SF is liquid. Therefore the fluid is continuously converted from fluid to gas. Okay, that's not that I told one. I said only the phase change duration. Okay, then dP by dt at saturation equal to hfg divided by T into Vf. This equation is called clapeyron equation. This equation is called clapeyron equation. dP by dt saturation equal to hfg divided by T into Vfg. Okay. In next unit we can see that curves, PVT and PV curves, Kachas curve, Kachaf curve. These types of curves are discussed in fourth unit. Okay, then at temperature relatively high but below critical point, Vg is very greater than Vf. Okay, Vg is very greater than Vf, because if we, for example, the density of water is 100 kilogram per meter cube. Density of water is 100 kilogram per meter cube. The density of steam is 1 kilogram per, which means that water occupies, steam occupies 1000 times of volume when it available in the liquid. Therefore, the gaseous volume is more greater than liquid volume. Okay, the gaseous volume is more greater than, because during phase change process, that the phase change means what? The intermolecular bond is breaked during the phase change process from solid to gas. Okay, then gas to solid is intermolecular bond force is attracted, but in solid to gaseous phase, the intermolecular force is continuously breaked. Therefore, the volume is continuously increasing. Okay, therefore the gaseous volume, same 1 liter, same 1 kg water and same 1 kg steam, both are occupying very different volumes. Okay, therefore the Vg is very greater than Vf. Therefore we can write Vfg equal to Vg minus Vf. Therefore Vf is negligible, therefore Vfg equal to Vg. And remember the PV equal to RT equation, then Pg equal to RT by P. And the above equation becomes dP by dt saturation equal to P into hfg divided by RT square. Okay, I substitute Vfg instead of, Vg instead of Vfg, that Vg equal to RT by P, then substitute things, then dP by dt is saturation is equal to P into hfg divided by RT square. Okay, this equation called Claudius-Clapeyron equation. Okay, this is only for Vg is very greater than Vf. The condition is Vg is very greater than Vf. Otherwise, the equation is Clapeyron equation alone, that is hfg divided by hfg divided by T into Vfg. This is a Clapeyron equation for liquid or gaseous phase. Considering gaseous phase alone, we neglect the liquid phase, then we can write the equation as dP by dt equal to P into hfg divided by RT square. This equation is called Claudius-Clapeyron equation. Once we integrate the equation, rearrange the equation, dP by P equal to hfg by R into dt by d square. Okay, then 1 by P, integration of 1 by P equal to ln P2 by P1, which is equal to hfg is a constant and also R is a constant. Then dt by t square is different, integration is 1 by t1 minus 1 by t2, not t square. Okay, it's a t2. Integration of 1 by t square or 1 by x square equal to minus 1 by x. Formula: integration of 1 by t square is equal to minus 1 by x is the formula. Therefore 1 by t square equal to minus 1 by t. Limit is t1 to t2. Therefore minus 1 by t2 plus 1 by t1. Then this is rearranged 1 by t1 minus 1 by t2. Okay, not t2. T square is a small printing mistake. So t2. Okay, the equation can be used more frequently. The Claudius clapeyron equation. Okay, in that only one topic is remaining. This Joule-Thomson coefficient, and after that we can start the fourth unit. Okay, thank you.